Okay, the recording is now going, just so everyone knows. It's official. It's 5 o'clock, so maybe just one more minute in case anyone is going to trickle in, and then we can get started. Okay, everyone. Thank you so much for coming tonight. I know it's like Friday of week 10 and finals are starting, so but we're just going to talk a little bit about linear algebra in the context of data science. And so I'm Igor. I'm a sophomore mathematics economics major and a minor in computer science, and I'm going to be presenting along with Ethan today.
Yeah, my name's Ethan. I'm a first year data science major, and let's just get started. Yeah. All right. So if you guys want to see the slides we're at, you can go to this URL. And yeah, we can send it right now in chat. I'll send it right now in the chat just so that everyone can have like quick, easy access to it. Right, so
All
just
right.
copy that link in your browser if you want it, and let's just keep on going. All right, so the agenda for today is we're first going to cover like what linear algebra is, and then we're going to talk about why it's useful in data science. And then we're going to show some basic processes in linear algebra like row reduction using both Matlab and Python, and also show transformers in both Matlab and Python. And then finally, we're going to talk about what you can do with all this knowledge in the future and how you can like research further on your own. All right. So, okay, so linear algebra is a branch of mathematics that has to do with systems of linear equations and manipulating and transforming these planes, vectors, and lines in 3D or higher dimensional space. And we deal with a lot of structures in linear algebra that come into play a lot in other computer science topics and data science topics, such as matrices, determinants, vector spaces, and linear transformations. And one of the key uses of it is machine learning, which we're just about to talk about next. All right. So these you can go to the next slide, Igor.
Mm-hmm.
All right. So a lot of the times in data science, we use matrices and other objects like those in linear algebra to represent data, and that's because they're oftentimes the most useful to represent these as matrices. And a, a lot of machine learning models use these matrices in order to interpret different, like, what's it called? Interpret the data, because all of the linear or the matrices can be represented as, what's it called? Just linear equations that the machine learning model can solve and eventually output like predictions from. All right, so here's an example of a matrix using the machine learning, a matrix using a machine learning, what's it called? Capacity. So as you can see here, the rows in the matrix represent all of the data columns, or not the data columns, like the data values, and then each column represents a different like feature, as they're called. So these features would have to do with like say one data point, like height or something like that, and then feature 2 could be weight. And if these were like describing athletes or something like that, then this matrix could describe like a whole team of athletes or something like that. And the machine learning models could use those in order to make their own predictions. All right, and here's just an example of a neural network. These neural networks are oftentimes used in machine learning, and they use simple data science, simple linear algebra and linear regression models a lot of the time in order to just create results. However, they do them many times, which is why they're called deep neural networks.
Okay, yeah. So Ethan just talked about some applications of linear algebra, essentially why linear algebra is important and why it's important to study if you're interested in data science and machine learning. And now we're just going to walk through some of the kind of simple elementary operations that are involved in linear algebra, the subject area. Um, because if you think about it, we're talking about matrices, it's really just a box of numbers, and they're convenient. People like them so much, or I guess mathematicians and data scientists, etc. People like them so much because you can just shove them full of all sorts of linear equations, like y equals 2x plus 4x2 plus 9x 3, and so on and so forth, for as much as you want. And row reduction is also known as Gaussian elimination, is one of the ways by which you can actually find solutions using these matrices. Solutions where you have, y equals, or x1 equals something, and then x2 equals something else, and so on and so forth. So this is kind of, you could call it the algorithm, or just the method by which you would find kind of solutions to all of the linear equations that are inside of your matrix. What that really entails is kind of, I'm just going to go ahead a couple of slides here. What that really entails is, if you see on the bottom right in the blue box, I don't know if I can use there's like a pointer or anything. I don't know, maybe, no. Okay, whatever. If you just look on the bottom right in the blue box, and then you look at the matrix on the bottom right inside the blue box, the one that says A R R E F, you see that we have a 1, and then to the below and to the right there's another 1, and these essentially indicate places where we can find solutions to linear equations. And the whole point of Gaussian elimination is to actually get to a matrix in row reduced echelon form, and that's going to look like this, where you have the first column has a 1, and it has no other non-zero entries below it. And then you move to the next, you move to the right, from left to right, so you move a column to the right, and there's a 1 below the preceding one with no other non-zero entries below that 1, and then you basically continue onwards to the left. But just to go back, the process, it's outlined here on the top, and I'm just going to walk you through this example in the blue box about how we would actually get to this row reduced echelon form. So we're given this matrix A, and we need to get it somehow to this form on the bottom right that's we like, and it's easy to read and easy to understand. First thing we want is to get the pivots. The first we want the first non-zero entry in the first column of the matrix. So we find the first non-zero entry. That's right here. It's in the second row of this first matrix A. Second row. So we can do a row operation called swapping. You can swap any 2 rows in a matrix. So we're gonna, as you can see, we're moving from A to A1, we swap row 1 and row 2. So now we have 1 2 1 on the top, and then 0 1 2 is now the second row. So we interchange the rows, and now when we move from A1 to A2, what you can see is that we use another kind of row Gaussian, I guess, a row operation. It's we just multiplied the top row by 2, and then subtracted that from the bottom row. So if you just look at the matrix A1, we're gonna multiply the top matrix, top row by 2. So we're gonna have 2, 4, 2 in the top, and then we're gonna subtract that from the bottommost row. So 2 minus 2, we end up with 0 in A2. 7 minus 4, we end up with 3, and 8 minus 2, we end up with 6. So that's how we get A2. And as you can see, that's outlined in the fourth bullet point. Add multiples of the pivot row to each of the lower rows. So every element in the pivot column of the lower rows equals 0. So we're already well on our way to having a row reduced matrix. We have that we already have in our first column that the only non-zero element is the one in the top left. Now moving from A2 to A3 or A, this is no longer A3. We're actually going to now be in what's called reduced echelon form, or row echelon. Can't remember, reduced row. I think it is row echelon form. We're going to do a similar kind of thing where we multiply. We're going to actually multiply the bottom row, or excuse me, yeah, we're going to multiply the middle row by 3 and then subtract that from the bottom row. So 1 times 3 is 3, 2 times 3 is 6, and then we're just going to subtract that, or the bottom row from that. So we end up with completely zeros in the bottom row, and then so that's, and now we are in row echelon form. It's actually written right there. It's row echelon form, and we basically just repeated that pivot process, that row reduction process, to get what is now row echelon form. Row echelon form, you can see this just means that with these pivot ones, we have only zeros below the ones. And you can still have non-zero entries above the ones, but you can't have non-zero entries below the ones. And now finally, to get it in reduced row echelon form, we need to process non-zero entries above each pivot. So basically what that means, if you look in the matrix labeled AREF, we need to get rid of that too. And we're going to use the same old row reduction process. Remember, we have either swapping available to us, or we can multiply in rows and subtract them from each other. So we're going to use multiplication and subtraction. So we're going to multiply the middle row by 2 and subtract that from the top row. So 1 times 2 is 2, 2 times 2 is 4, and we end up with this nice matrix A row reduced echelon form, where we have we get rid of that 2 above the middle one. So that's kind of is a long-winded explanation of how to do row reduction, but it's if you do just have a pencil and paper, you'll be able to blow through these pretty quickly, and if you have Matlab to do it for you, it's even faster. But so yeah, let's just, as a little exercise, we can try to figure out which are in echelon form and which are in row reduced echelon form. So we want to identify the pivots. So the pivots would be the first non-zero entries in each row. And we can see that the row reduced echelon form would be this top matrix on the left. We have this nice sort of like triangular shape, triangle of zeros below the pivot ones. This matrix doesn't have that kind of perfect diagonal pattern. And the matrix on the top right, it's not in any kind of, it's not in echelon form, and it's not in a row reduced echelon form either. It doesn't look like it has had any row reduction applied to it. So this is like a word problem, I guess you could call it, on how to do row reduction. So I'll just read it out. So tickets for a Doja Cat show went on sale, and they were selling great until Doja announced that DaBaby would also be performing with her. So ticket sales severely plummeted so badly that the entire marketing and the sales team quit and joined Twitter. And you only know the ticket sales and money made, considering the whole team is now at Twitter, and we all know how that goes nowadays. So, how we can figure out how much they were selling the tickets for, and we're given some information about the tickets. So on the first day of ticket sales, they were going for they sold 68 adult tickets and 43 student tickets for a total of $5,385. And on the second day, they had $4,948 worth of tickets, and they sold 72 adult ones and 28 student tickets. So you can kind of, put together a nice little a system of two linear equations that I'm sure you guys have done many times in high school. And now with our little little knowledge about matrices, you can actually, this is what I was talking about earlier, where you can just kind of put these systems of linear equations and shove them into boxes, which we call matrices. So you see that 68, 43, and we have to the right of that 5,385. And you can see that each row corresponds to a variable, right? So the column. So the column with 68 and 72 corresponds to the x variable. 43, 28 corresponds to the y variable. And on to the right of that, we draw a dashed line to indicate the kind of the equality there. So we can use row reduction. Here's the process on the right. It's a little messy to do by hand because the numbers are kind of large. They don't divide very nicely, but it's really the same process that I showed to you earlier. So we're going to try to, first of all, always try to get that one in the top left. So we're just going to divide everything by 68. You can see we have 68 in the top left. So to turn that into one, we're dividing it by 68. And whatever you apply to the first element needs to be applied to everything else in the row. Okay, because it's an equation. You can't you can't just divide one thing. You have to divide everything. And now we're just gonna subtract row 1 multiplied by 72 from row 2. So we're gonna multiply. We're gonna multiply 72 times R1 and then subtract that from R2. And that's how we get this nice 0 that we like to see in the bottom left. And then after that, we're going to multiply row 2 by negative 17 over 298. That's because we want the next pivot, we want that to be the 1. And in order to get we have like this really ugly number, negative 298 over 17. So to get that to be a 1, we just multiply it by the inverse. So everything in row 2 is multiplied by negative 17 over 298. And finally, to get rid of the 0 that's above the second pivot, we're just going to do another little multiplication and subtraction. R1 equals, so we're going to R1 equals R1 minus 43 over 68 times R2. And we end up with this matrix here. And the way to interpret this would be to be that x equals 52 and y equals 43. Remember that the first column corresponds to x variable and the second column corresponds to the y variable. So x equals 52, y equals 43. So that's how you would do that. And you're probably looking at me like, why would I ever want to do that by hand? And luckily we have tools that can do that for us. So we can, if you haven't, I know they teach in Math 20D to use Matlab. I'm sure there are other classes on campus that also require you to learn some Matlab. So, but this is pretty straightforward. You just open up the terminal and you type in doja. That's just a variable name. Let doja be this matrix with two 2 rows and 3 columns. And then we have this command rref, and that'll just do all the row reduction for us that we just worked so hard by pen and paper to do. Matlab will just do it by command. Okay, and we already talked about how to interpret the results. So okay, and here's the Python example. I think you wanted the screen share, right, Ethan?
I actually can't screen share, so can
Oh,
you?
okay, yeah, sure.
All right, but I know that oftentimes it's kind of oftentimes like as data scientists we use Python, and so there are examples of how to do this in Python. So I have a Google Colab right here, which is basically a Python Jupyter notebook that you guys can follow along with, and I sent it in the chat. And yeah, so Igor, can you pull that up for me?
Sure. Yeah. You should have screen sharing privileges as well by now. But I
Oh,
can
okay.
also
I see
pull it
it.
up for you.
I see it.
Okay.
Let me go to it. All right. So, if you guys can see my screen, this is what the Google Colab notebook looks like. And so, let's just go over through that row reduction example that Igor was just talking about. So, Python doesn't have a built-in way to multiply these matrices, so we have to import a library that has this functionality. And an example of that is SymPy. So if we just import that, it might take a second as it gets connected. But yeah, so we import that first, and then we have to create the matrix. So often in code, matrices are often represented as arrays of arrays. So it's like a list of lists, and each list or array is a column or is a row, and then they're like stacked on top of each other. So you can think of this as a 2 by 3 matrix because it's 2 down, right? It has 2 down if you stack them right on top of each other, and there's 3 items in each row. Okay, so we have to establish this matrix, and then SymPy has a built-in what's it method for creating or transforming matrices into row reduced echelon form. And so all we have to do is just call that method onto our matrix, and it'll give us the answer. So as you can see right here, it's the exact same thing as if you had done it in Matlab or by hand, except it's a lot faster. All right, and obviously this is the interpretation as Igor was just talking about. All right,
All
Igor, you
right.
want to take over now?
Yeah. Yeah. Let me get the screen share going again. If you want, I think you're still okay. Perfect. All right. Okay. All right. We're going to talk about some linear transforms now. This is really kind of an essential part of linear algebra as well. It's kind of where some of the fun comes in. If you could call linear algebra fun, I guess. Okay. Um, so what is a transformation matrix? So it's a matrix, and it's a matrix by which you can transform other matrices in the sense that you can kind of change what's inside the matrix. That's all that means. So, okay, so matrices allow arbitrary linear transformations to be displayed in a consistent format suitable for computation. And this allows for transformations to be composed easily. Um, Composed meaning you multiply them together. So for example, we have here r of theta. Now this r of theta is just what's called a rotation matrix, and it will actually rotate the matrix by however many theta degrees you can indicate. So you want to rotate it by 90 degrees, you say put in pi over 2 and then multiply this matrix by another matrix that you want to apply the rotation to. Now, the, give you some intuition, I always found it useful to kind of think of a graph. So consider just a two-dimensional space, right? So we have this XY plane on the bottom right. And that can be, so we have some point XY on this linear line that's pointing away from the origin. XY can be represented as a matrix. Um, that's kind of the beauty of linear algebra. You can take uh, points, you can points in 2D spaces or whatever dimensional spaces and represent them as matrices. And all you need to do is multiply our rotation matrix by your point xy, and it's going to apply the rotation. So that's kind of the graphical intuition there. And there's a lot of use cases. Just to list a few, so vectors represented in 2 or 3 dimensional frames are transformed to another vector. And then we also have the linear combinations. So linear combinations of 2 or more vectors through multiplications are possible through a transformation matrix. Linear transformations of matrices can be used to change the matrices into another form, kind of like how I just showed. You can move around the graph, a linear graph. And matrix multiplication, determinants, inverse spaces are achieved by matrix transformations. We have dot products, change of basis vectors. These are all things that you're going to learn about if you take Math 18 or the honors class. But yeah, there's basically linear transformations are very fundamental. I think is just what we're trying to say here. Okay, so yeah, what is a transformation matrix? I kind of explained it. This is your transformation matrix is this R of theta. This is what is actually doing the transformation and taking your point xy and transforming it to point x prime y prime. So that's kind of the idea there. And again, Matlab has cool tools that can do these kinds of things for us. So we have, if you look in the documentation, we have this function rot x, and then you give it the angle you want. So like it says at the top there, if you want to rotate a matrix by 90 degrees, we just use rot x and we pass it 90 degrees. And yeah, it creates a 3x3 matrix by rotating a 3x1 vector or 3x(n) matrix of vectors around the x-axis. So that's just kind of mechanically describing what the rotation does. And so this is so Matlab has we've just given it the command r equals rot x, and we've given it 90. So our r for a 90-degree rotation, this is what r looks like. If we multiply if we multiply a matrix by r, it's going to rotate it by 90 degrees. And this is exactly what we do. So we have ds3, the matrix 1 1 1, and we multiply to the right. We have r times ds3. That's just multiplying 2 matrices together, and you can see that 1 negative 1 1. If you were to graph this out in the 3D space, it's rotated 90 degrees. Yeah, so there you go. There in the blue we have the original matrix, the original vector, and in red this is the matrix that's been rotated by 90 degrees, all thanks to us multiplying this little R matrix R by this 90-degree rotation matrix. Okay, now the Python demo. All right.
Yeah, we can do the exact same thing in Python. It's a little more complicated because Python doesn't have these sorts of things built into it like Matlab does, but we can get the same thing done. So first we have to import 2 different libraries. One is matplotlib and the other is numpy. So matplotlib is just for plotting it and for graphing the outcome of our multiplication, and the numpy is a library that supports arrays as well. So just like SymPy, it also has functionality for arrays. And so we can also make matrices out of those arrays. All right, so first we have to import these, and after we import them, we have to create these matrices. So as you can see here, my transformation matrix is the same one that was in Matlab, except here it's all in a single row instead of being like laid out like one on top of each other. So once you create your transformation matrix, which is the 90-degree rotation matrix, we can then uh, make our vector that we're trying to transform. And that's just a 3 by 1 matrix here, as you can see right here. And then NumPy has a built-in, what's it called? Built-in method called matrix multiply. So it's or matmul. And all you have to do is just list the two vectors that you want multiplied in the order that you want them multiplied in. So we're going to have our transformation matrix on the left and our vector on the right. And then you can see here that our transformed vector, which is the result of this, is the same thing as what we got in MATLAB or if we did it by hand. And then we can just plot this using matplot.lib, matplotlib, and this gives us a vector. And the two vectors side by side rotated. All right.
All right, I'll screen share again and we can finish out. Okay. So yeah, that's kind of, I hope this workshop has been able to give you kind of a little bit of a outline about of what linear algebra is about, in terms of the subject matter. Many of these things, if you've already taken a linear algebra class, I'm sure you're already very solid on what row reduction is, how to get a row reduced echelon matrix, what are transformations, how do they work, why do they work. But hopefully this workshop, even for those of you who have taken those linear algebra classes, as you can see, there's a lot of tools out there, like Ethan has shown you guys, that can really help simplify your life, so you don't have to do all these calculations by hand. And you can see how if you kind of harness these tools, you can do thousands, tens of thousands, just huge amounts of calculations. And kind of those kinds of tools, they form the foundation of machine learning. Some fantastic resources. So I really highly recommend the YouTube channel 3 Blue 1 Brown. He doesn't just make videos about the linear algebra, he makes videos about other sub-subjects as well. But I definitely started watching him when I took linear algebra, just because he really helps give you the kind of foundational intuition for how things work. Because I felt like when I was learning linear algebra, you're just looking at a box of numbers on a page, and it doesn't have any meaning, but there's actually a lot going on there, more than maybe meets the eye, and he has all these cool animations that lay it all out for you. There's a textbook as well, if you're more of like a textbook kind of person, you like reading old fashioned, and a row reduction calculator, of course, those always come in handy. And yeah, are there any questions of any sort? It doesn't even have to be about linear algebra, it could be whatever.
Yeah, it can be more about how like matrices are used in machine learning or anything like that. Doesn't look like there's any questions. So yeah, I guess we're just done for today then. Just reach out to either of us if you want to, and or Lauren, who's the director or the leader of the math workshops team.
Yeah.
And
Yeah,
yeah,
definitely want to thank Lauren for putting together the lesson plan for today. did a fantastic job with the slides and with the logistics. So yeah, big round of applause for Lauren. Yeah. All right, yeah. Thank you guys so much for coming. And we hope you guys have a great rest of your evening and good luck on all of your finals. Oh, I see. Sorry, Edwin. I see your question. I think everyone left before. Uh, so you're new to the organization and doing data analytical research. Um, I'm relatively new to the organization as well. Um, can you hear me okay, by the way? I just want to make sure I'm getting my answer across. Okay. Yeah, so I'm relatively new as well, so I don't know. It's a pretty big organization. DS3, there's a lot going on and I feel like it's growing a lot in recent times, but I'm positive that the group can help you with machine learning questions. There's a lot of really talented people, especially people in their junior and senior years who have had more exposure to those kinds of topics. So um, I encourage you to reach out on the Discord, perhaps, and maybe next time we have an in-person workshop, you could come and um, meet Lauren in person. I'm sure he can point you in the right direction as well. Um, okay, yeah, yeah, perfect. So yeah, all right, yeah. Have a good night. Thank you.